All right, it's time to do a normal tangential problem. So here's the problem we're going to have. I have an automobile coming around a circular curve. As it enters the curve at position A, we're still at the straightaway, I have a velocity of 20 meters per second, and that's purely tangential because we haven't made the curve yet, right? That's purely tangential, so it's in the horizontal here. I am speeding up with an acceleration of 2 meters per second, right? My speed is increasing by 2 meters per second each second. So I have an acceleration, and it's purely E tangential at this point as well. But when I get to point B over here, at point B, I'm going to have a different velocity because, first off, it's changed direction, but it's also getting faster, so it won't be 20 anymore. But then I'm going to have an acceleration, and it's going to have a component forward, and that'll still be 2 meters per second squared. That hasn't changed. So the component of the acceleration in the tangential direction will still be 2. But in the normal direction, I'm going to have some other acceleration equal to v squared over rho. Right? So v squared over rho. Now my rho, or r in this case, is 50 meters. So the question becomes, how do I get this? Well, it's simple kinematics as I go from A to B. I'm moving along a curve, yeah, but that's one-dimensional. It's in the s direction, or negative s direction. So it's really one-dimensional. So I could use one-dimensional kinematics, and one-dimensional kinematics says, hey, S equals V tangential, which it's all tangential, right, times T plus 1/2 A tangential times T squared. And I really need to put in an S naught here, right? So I'm going to assume that S naught is equal to 0, so that's going to be 0. So I get some distance, I don't know, but I'm going to find that in just a second, equals 20 meters per second. That's the initial tangential velocity, speed, plus 1/2 the tangential acceleration times t squared. Because this is being affected fast and slow, it's being affected only by the tangential acceleration, right? The normal acceleration doesn't affect the one-dimensional motion along the curve. Okay, so S naught is equal to 0. What's S? Well, I have a 45-degree angle. That's pi over 4, so S equals r theta along an arc length. You might remember that from geometry. R is 50 meters, theta is pi over 4 radians, right? And so if I work this out, I'm going to get 39.27 meters, right? S equals r theta, I get 39.27 meters. All right, so let's find the time. So what do I have here? I've got, let's see, I've got a distance of 39.27 meters, and that's going to equal, the initial position was 0, so it's going to equal 20 meters per second t plus 1/2 2 meters per second squared t squared. Right? Sorry about that. Got there a little crowded there. All right, so that's going to be 39.27 meters equals 20 meters per second t plus 1 meter per second squared t squared. So let's bring the 39.27 over here. Right? And on the left-hand side of the equal sign, I'm going to put a 0. And this is a quadratic. And when you solve this quadratic, you get two solutions. One of them is negative, so that's not reasonable. It doesn't make sense. So that we throw that one out. But the other one is t equals 1.8 seconds. And so the time to go from A to B is 1.8 seconds. Well, if I keep that in mind, then I can figure out my speed after that 1.8 seconds. I started off at 20 meters per second, so my speed equals 20 meters per second plus 2 meters per second squared times 1.8 seconds. Right? And so that's going to be 3.6, and so I get 23.6 meters per second. So that's my speed at B, and it's all tangential. It's all tangential. So if I want, I could write the velocity at B. The velocity at B equals 23.6 meters per second E tangential. And so there's the vector value. Then the other thing I'm interested in then is v squared over rho, right? The normal component of the acceleration. But that's going to equal, so let me just say A normal, and that's going to equal v squared, which is 23.6 meters per second, square that, and divide that by 50 meters, right? And if I do that, I get 11.14, and that's going to be meters per second squared. Meters squared per second squared divided by meters is going to be meters per second squared. So it's pretty substantial acceleration. That's more than the acceleration due to gravity. So you're feeling that as you go around that curve. And so I could write my acceleration then. My acceleration at B would equal 2 meters per second squared E tangential, that's how it's speeding up, plus 11.14 meters per second squared E normal. That's the normal component of the acceleration. And so there's my position, my velocity, and my acceleration in the normal tangential system. Can I convert all this to an XY coordinate system? Absolutely. And we'll do that in another lecture. All right. Any questions on this? Leave them in the comments and I'll get back to you as soon as I can. Thank you.